Okay, so the shape that we eventually end up making, if we went to infinitely many shapes, is going to look something like this.
Yep.
And I found this on Thingiverse, and it actually has a name. It's called the Gosper Island, or the Gosper Curve. And it's pretty incredible, actually. So pretend this has infinitely many crinkles, even though, why couldn't we 3D print infinitely many crinkles?
Because it would have to be infinitely thin.
Yeah, it would have to be infinitely thin.
I don't think the 3D printer has that setting, though.
Yeah, I don't think our 3D printer has an infinity setting. Be cool if it did, though.
Yeah.
Although it might take a while to print things.
Yeah.
So here's the amazing thing once you go to infinity on this. So I start with one in the middle. You see the one in the middle?
Yep.
And I put the shapes around it. Now what's amazing, remember we said when you go from infinity to infinity plus 1, you have the same shape?
Mm-hmm.
Well, this is from one step to the next step, right? So that means the boundary of this shape is the same shape as the boundary of this shape. That wasn't happening before, right? When we went from the hexagon,
Definitely wasn't. No.
it definitely wasn't. So can you sort of see that the boundary of our big shape is the same as the boundary of this shape?
Yeah, it's looking more and more similar as you get bigger and bigger.
It looks like it.
Yeah.
It definitely looks like it. You can kind of see if we spread them out just a little bit. You can see how this one kind of has a point that kind of pokes out a little bit, and it corresponds to a point that pokes out there. And then you wiggle down into a valley, then back up and around, you know, you see that?
Yeah.
So it's the same sort of shape, even though I may not have explained that exactly perfectly. But, and it's what we said before, when you have infinitely many sides, the boundary is the same.
Yeah. Alright.
Okay? But how much longer is the boundary around here than it is around here?
If the boundaries are infinitely long, then they should be the same.
That's interesting. What do you think, though, if you went around this shape here and you went around that shape there?
Well, how much is... It looks to me, at least, like this portion of the perimeter of this shape is about half of the perimeter of the whole shape. Like this part here and this part here are the same.
I'm actually not quite sure what you're saying.
So I'm looking at the perimeter. If you look at...
From there to there, okay.
So look at that part.
Yeah.
I think it's the same as looking at this part underneath it.
Ah, okay. So that to there is halfway around one of our single shapes. Okay, I see what you're saying. That's interesting.
So that means, and you have 6. That means the perimeter should be around 3 times the perimeter of that.
Okay. Do you see that?
Yeah.
You go, that's a great observation. So when I go from here to here, it looks like I've gone halfway around the shape, and then halfway around. So now that's once around.
And then
1.5.
2, and 2.5, 3.
3. Wonderful.
Yeah.
Wonderful. And another way you could kind of see that we've scaled this up by a factor of 3 is if you pretended I had a center point here. Like there was the middle of this, and I went out to here.
Yeah.
And let's call that the radius. Now, how many of those radiuses do I have when I go all the way out to the edge of this one?
And you have 3.
3. I have a total of 3. I have 1, 2, 3. So I've scaled this by a factor. This interesting shape. I've scaled it by a factor of 3. Now, what happens to the area of a square when I multiply the side lengths by 3?
The area gets multiplied by 9.
What happens to the area of a triangle when I scale it by a factor of 3?
It's still multiplied by 9.
What happens to the area of a pentagon when I scale it by a factor of 3?
Still multiplied by 9. It looks like any two-dimensional polygon would work.
Looks like any two-dimensional polygon's area would scale by 9 if I scaled the lengths by a factor of 3.
Yeah.
What happened here? What happened to the area of this shape when I took one of them and then I scaled it by a factor of 3? What happened to the volume?
You mean the area?
The area, sorry.
It gets multiplied by 7. Wait.
What do you think?
Wait, it gets multiplied by
6, wouldn't it be?
1, 2, 3, 4, 5, 6, 7.
What do you think? You're looking puzzled.
Hmm.
What do you think happens to the area?
Well, you're adding 6 more on.
Okay, so how many of them do I have in the big shape?
And the big shape you have 7.
And how many do I have in the original shape?
1.
So what happened to the area?
It got multiplied by 7.
But it seemed to be scaled by a factor of 3.
But 7 is
Shape
prime.
weird.
So what do you think's going on? It should have been, seems like it should have been a factor of 9. But we got a factor of 7. What do you think?
But 9 doesn't equal 7.
No, 9 doesn't equal 7, just like what two numbers are not equal?
Like 3 and the square root of 7 aren't equal.
Okay, what else did we see today, two numbers that were not equal?
And we saw that the numbers that we scaled by.
We saw something today, two numbers that someone showed were equal, but they aren't equal.
Oh yeah, pi
and
and 4.
Pi and 4 were not equal.
This may be the same kind of trick
What's going on?
where you're.
What's similar about these two situations?
There's an infinity of something in
Okay.
both of them.
Infinity of what?
Infinity, well, in this, there's infinity peaks, and then in the other one, there's infinity peaks too.
So we somehow had some sort of weird infinite crinkles here. And it caused the scale factors to not work the same way we thought.
Yeah.
And in the other one, it caused an argument that looked like pi should equal 4, but it's that we know that's not right.
Yeah.
So here we saw what? What did we see that we didn't expect here?
We saw
that
it was
scaled by a factor of 7 instead of 9.
And does that seem strange?
Yeah.
Very strange.
So what we're seeing in these two examples of pi equal 4 and then the scaling here is that infinity has some weird properties.
Yeah.
You would not expect this to be the same shape but scaled by a factor. Area scales by 7 when you make it 3 times as large.
No.
That seems to be what happened.
Yeah.
What do you think?
I don't know. Strange.
Do you think that's cool?
Yeah.
Yeah.
Pretty cool. I wonder if any other shapes do it. Maybe some other shapes with infinity involved.
Yeah.
Like the Coke snowflake, maybe.
The Coke snowflake has an interesting sort of similar property, and other shapes like similar to this are called fractals.
Yeah.
Fractals, yeah.
And we've studied a couple of fractals before.
Yeah.
Anyway, pretty neat, I think.
Yeah.
This is one of the coolest things. I never knew about this shape until just the other day.
Me neither.
Pretty fun.
Yeah.
All right. High five, guys. Good project.